Hey guys, today we're going to be learning about cubic functions. Now a cubic function is any equation or functions equation where the highest exponent is to the third. So today we're going to learn how to graph it, how to write the equation of a cubic function based on the graph, and how to solve a cubic equation. So first we're going to investigate the parent function, which remember that the parent function is the original, the one without any transformations. So the parent function for the cubic function is x to the third, with nothing added or subtracted or multiplied, divided to it. In order to get the reference points, I've given you here a table with all of these x values. And in order to get the y values, we need to take this number and plug it in. So if we plug in -2, that's -2 to the third, which any number raised to the third power means that we multiply it with itself 3 times. So -2 times -2 times -2 is -8. If I do the same thing with -1, -1 to the third is -1 times -1 times -1, which is -1. 0 to the third is just 0. 1 to the third is 1. And 2 to the third is 2 times 2 times 2, which is 8. So these are going to be my reference points. I'm going to take these coordinates here now and plot them on my graph. So we have -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. When I connect any polynomial function, because a cubic function is considered a polynomial function, it has smooth curves. So it would look like this. So that means that all of the graphs that we're going to be looking at today are going to have this general shape. Now we're going to go back to some older material that we covered earlier on in the year and figure out these particular attributes of the graph of x cubed. Remember that the domain is the set of all the x's that are included in the graph. Even though it's hard to see, we can see that this graph here will eventually open up to the right forever. And this part here is going to open to the left forever. So that means that if I were to extend to the left forever, that's towards -infinity. And to the right forever, that's towards +infinity. So the domain would be -infinity to +infinity. Remembering that we learned 2 ways of writing intervals. We learned set notation and interval notation. Set notation is the one that involves an inequality, and interval notation is like this, where you write from where it starts to where it ends, and we use brackets and parentheses to indicate if a number is included. Now to move on to the range. The range is the set of all the y's. So if I look at this graph does go down forever, and it goes up forever, making the range -infinity to +infinity. End behavior is how your graph is behaving at the ends. So this is the left side of the graph, and this is the right side of the graph. Keeping in mind that when we're writing end behavior, we always write our 2 statements. As x is approaching -infinity, that means the left side of the graph. The left side of the graph here is going down, so f of x is approaching -infinity. If I were to look at the right side of the graph for as x is approaching +infinity, on the right side of the graph, f of x, my y values, are going up, so it's going towards +infinity. Whenever you're asked for the zeros of the function, that just means the x-intercepts. So when I look at my x-axis, my cubic function intersects the x-axis at x is equal to 0, which is also the origin, so you can also write it as a coordinate 0, 0. Now the function has positive values. When you're being asked where the function has positive values, that means from what x to what x, and positive values means the y values. So if I look at my graph here, my graph will have positive values as long as it is above the x-axis. So this is where my graph is positive. And so when I write my interval, we start at the x where it starts positive, which is at x is equal to 0. And then it's positive the rest of the way towards the right, so towards positive infinity. The function has negative values when it's below the graph, so the part here that I did not highlight. And it's below the below the x-axis, the whole left side of the graph. So we would start from negative infinity until 0, because then at 0 it becomes positive. Now if I were to trace my graph from left to right, notice that the entire time I am going up. So that means that my function is increasing the entire graph. So that's negative infinity to positive infinity. The function here, since it's going up the entire time, it is never decreasing. So you can write the null set, which is indicated by a 0 with the horizontal line through it, meaning that it's never decreasing. Now let's look at how to graph these cubic functions. Here we have g of x is equal to 2 times x minus 1 cubed minus 1. For the purposes of this lesson, right, notice that in the previous slide, when we were looking at our reference points, we had these 5 coordinates. Now we don't necessarily need to use all 5, simply because it would be a lot more work, and also the farther away you get from the vertex, which is here at the center of the graph, the higher those numbers become, which may go off the graph that we are given. So we're only going to use these 3 middle points, but keeping in mind that your graph does have to have this shape every single time. So when I look at this equation, first let's identify the transformations, keeping in mind that anything inside the parentheses affects the x, and anything that is outside of the parentheses affects the y. Based on the equation, I can say that there is a vertical stretch of 2 because of this 2 here. Since it's being multiplied on the outside, that means that the y values will get bigger. So vertical stretch. This minus 1 means that it's going to go to the right 1. And this minus 1 at the end means that the graph will go down 1. Now we're ready to write our transformation rules. So remember, we start with xy to indicate the original points. The rule for the x's, remember that we switch whatever it says to do inside the parentheses. So we would write x plus 1. Everything outside affects the y's, so the rule would be 2y minus 1. We have our reference points, -1, -1, 0, 0, and 1, 1. These points are very similar to the ones that we use in the quadratic, but in the quadratic we use -1, +1, since the quadratic is always positive. In this case, just remember that the only reference point that changed is the -1, -1. So when we plug it in, -1 plus 1 is 0, 2 times -1 is -2, minus 1, -3. When we plug in 0, 0, 0 plus 1 is 1, 2 times 0 is 0, minus 1, -1. And when we plug in 1, 1, 1 plus 1 is 2, and 2 times 1 is 2, minus 1, 1. So these are my coordinates, and I'm going to go ahead and plot that now. So we have 0, -3, 1, -1, and 2, 1. When you put your 3 points on the graph, it looks like a line. But remember that this is the cubic function. So that means that our graph has to have that curve. So we would graph it like this. You curve it, and then you curve it back down. And that's my cubic graph there. Let's try a few more. By looking at the equation, anything that is inside of the outermost parentheses affects the x values. So my transformations here, first off, I have this negative on the outside. A negative on the outside indicates a reflection across the x-axis. This 1/2, remember it's inside of the parentheses, so it is a horizontal stretch. of 2. Since we always do the opposite, 1/2 means divide by 2, and the opposite of division is to multiply. And when we multiply, those x values will get bigger. So that makes it a stretch. Next, we have this minus 3, meaning that my graph will go to the right 3. Now let's go ahead and write those transformation rules. The rule for the x's, remember we do the opposite, so instead of 1/2 we would say 2x plus 3. And for the y's, the only thing that's affecting the y is the negative, so negative y. Now we use our reference points, -1, 0, 0, and 1, 1. We plug in these coordinates. When I plug in -1 for the x, 2 times -1 is -2, plus 3 is 1. When I plug in -1 for the y, -1 makes it a positive 1. When I plug in 0, 0, 2 times 0 is 0, plus 3 is 3, and -0 is just 0. And finally, when I plug in 1, 1, 2 times 1 is 2, plus 3 is 5, -1. So these are my 3 points. I'm going to go ahead and plot that now. 1, 1, 3, 0, and 5, -1. Remembering our curve here. So it always starts like that, and then it'll come down. So this is my graph. Notice that when we have a reflection, my graph now is decreasing the entire time. Let's see what happens in this equation. We have g of x is equal to negative on the inside, x plus 1 to the third plus 2. This negative on the inside of my outermost parentheses affects the x's. So if my x's switch signs, that means that it is a reflection on the y-axis. This plus 1 on the inside means that my graph is going to go to the left 1. And the plus 2 on the outside means that it's going to go up 2. Now let's write our transformation rules. We have xy. The rule for the x's, remember negatives are the only exception. Even though whatever is inside, we always do the opposite, the negatives will always stay there. So we have -x minus 1. And the rule for the y's is just y plus 2. So now we have our reference points. And we plug in those numbers. -1 makes it a plus 1, minus 1, 0. And -1 for the y, -1 plus 2 is 1. When I plug in 0, 0, 0 minus 1 is -1, and 0 plus 2 is 2. Finally, when I plug in 1, 1, -1 minus 1 is -2, and 1 plus 2 is 3. So now I can plot these points. 0, 1, -1, 2, and -2, 3. Remembering to curve. Look at both of these graphs. Notice that whether you have a reflection across the x-axis or a reflection across the y-axis, the orientation is the same. It's always going to be decreasing. And that's something to keep in mind for the next part of this lesson, which is that we're going to write the equation of a cubic function now based on the graph. So we're going to be working backwards here. Now this is the general form of a cubic equation. There should be an extra parentheses here, sorry. Now I don't typically like to remember anything more than I have to. I don't like to memorize. But if you like to have a format, this is how you would write out the equation for a cubic function, where A represents any kind of vertical dilation or reflection on the x-axis. 1 over B represents a horizontal dilation, or if there's a reflection on the y-axis. A horizontal shift or translation is the H, and a K is if there was a vertical shift or some kind of vertical translation. So in order to be able to write the equation, we need to examine what kinds of transformations took place on this graph. And so I have here these 3 questions that you can ask yourself in order to figure this out. First, we look at how did the vertex move? Remembering that when we look at the first slide here, I had indicated that the vertex is that point right in the middle of the graph. So that 0, 0. So we're looking at the same thing here. The vertex is located right here. It's that middle part of the graph where it changes from like this little hill here to this little dip there. So this is my vertex. Since my vertex is located at 2, 1, and it's originally at 0, 0, that means that my vertex moved right 2 times and up 1. Now here we're going to check if the graph flipped. Notice that this graph is always increasing. If it was decreasing, just like we saw in the last 2 examples, whether you have a negative on the inside or on the outside, the graph will always be decreasing. Since my graph is increasing, that means that there is no reflection. So in order to check whether this graph has a reflection, we're checking whether it is increasing or decreasing. If it's increasing, there's no reflection. And if it's decreasing, there is a reflection. And it doesn't matter whether you say it's a reflection on the x or the y, because as we saw in the previous 2 examples, it would look the same. Now the next part is to check if there are any dilations. And the way you do that is you pick a point that is either to the left or to the right of the vertex. Doesn't matter the direction. So let's say I choose this point. But you could have also used this point. What you do is you compare the horizontal distance to that point with the vertical distance. On the parent function, the horizontal distance and the vertical distance is 1 away. This horizontal distance is 1 unit, and this vertical distance is 3 units. As you can see, this changed. It's no longer 1. It changed to 3, and that's the vertical distance. So this indicates that there is a vertical stretch, since now that distance is 3. So it increased. If the distance was less than 1, then it would be a vertical shrink. But this is a vertical stretch, and it's a vertical stretch of 3. So now we're ready to write the equation, and this is what I typically do. I know that my equations will be g of x is equal to, and then I'm going to have my parentheses with x to the 3rd. This is how I always start it off, because this is how we typically write those equations. We have parentheses, we have the exponent, and we have x inside of that parentheses. Then I start putting in those transformations into my equation, how it should be written. Write 2, we normally write it inside with the x, and we write the opposite of what it says. So we would write here minus 2, and that means it went to the right 2. Up 1, that's a plus 1 on the outside. No reflection, so we don't have to worry about putting a negative anywhere. And then there's a vertical stretch of 3, and that is typically a number that is written outside of the parentheses to the left of it and multiplied. So we would write the 3 like that. And this would be my equation for that particular graph. Let's look at a couple more examples. Here we have the graph of some cubic function. First, we want to identify if there are any transformations, or rather translations. And the first thing that we do is we locate the vertex. The vertex is here at -2, -2. Now, keeping in mind that the original cubic function, the vertex is located at 0, 0, that means that this graph shifted to the left 2 and down 2. Next, we identify if there is some kind of reflection. And how we do that is by checking whether this graph is increasing or decreasing. If I read the graph from left to right, my graph here is decreasing. If the graph is decreasing, that means that there is a reflection. If it was increasing, that means that there would be no reflection, since the original graph for the cubic function is always increasing. Now, we don't necessarily know if this is a reflection on the x or on the y-axis, and it doesn't really matter what you say, because whether you reflect on the x or on the y is the exact same graph, and let me show you why. This is your cubic function, the original graph, and you see how it is always increasing. If I say that there is a reflection on the x-axis, that means that the negative is outside of the x. And we see that it is flipped. Now it is decreasing. Now let's see what happens if I put that negative inside with the x, meaning that there is a reflection across the y-axis. It is the exact same graph. So whether you put the negative on the inside or on the outside, it's the same thing. So we don't have to specify whether there is a reflection on the x or the y. Just know that there is a reflection and we're going to have to include a negative inside of my function. So now we have to check if there's a dilation. And in order to do so, we need to identify one other point on this graph. It doesn't matter which one you choose. You could choose this one here or the one down here. And what you do is you check for the horizontal and the vertical distance from one point to the other. This horizontal distance here is 1, so there is no horizontal dilation. But the vertical distance here is 3, indicating that there is a vertical stretch of 3. Now how do we write this equation? We're going to set this up just like the others. We're going to open parentheses, x cubed, and now we're going to fill in with the rest of the information. Left 2 means that we would write plus 2 inside of the parentheses. Down 2 means I would write minus 2 at the end. A reflection means that there is a negative. Now if you choose to put it on the outside, it would go right here. And a vertical stretch would mean that a 3 is multiplied on the outside. So like this. So this is my equation. Another possibility would be 3 for the vertical stretch, parentheses, and then if I decide to put the negative with the x, we would put the negative here, but then we would have to open a second set of parentheses for the x plus 2. So both of these are acceptable answers. So just again to reiterate, if you have a reflection on the y-axis or any kind of horizontal dilation, we need that second set of parentheses and you would write those numbers in that little space. Let's try this other one here. For this particular graph, the vertex is located at 1, 1, indicating that my graph shifted to the right 1 and down 1. Now this graph is always increasing. So since it's always increasing, that means that there is no reflection. Now to check for any dilations, I'm going to choose another point. So let's just say this one, but you could have also used this one here, whichever one you prefer. I'm going to check for that vertical and that horizontal distance. My horizontal distance is 2, which means that there is a horizontal stretch of 2. My vertical distance is 1, meaning that there is no vertical dilation. So now let's put this in our equation. I'm going to open my parentheses here, cubed. Right 1, that means I'm going to put minus 1. Down 1, I'm going to put that minus 1 on the outside. There's no reflection, so I don't have to worry about that. Now because that there is a horizontal stretch, remember that we have to open a second set of parentheses to write that. So I'm going to open my parentheses here, and that means I would have to have a second set there, so that x minus 1 is enclosed. The horizontal stretch, when we put it inside of the parentheses, we have to write the opposite, or rather the reciprocal of the stretch. So instead of 2, I would write 1 over 2. And this would be my equation for this particular graph. Now we're going to shift gears a little bit and we're going to look at how to solve a cubic equation algebraically. So in this equation we have negative x plus 1 cubed plus 2 is equal to negative 25. What we're going to do is we're going to try to isolate that x value. So first we would have to make sure that we get this part here isolated, the part that is cubed, because then we would need to cancel out that exponent. So we're going to remove everything else that's around it to the other side of the equal sign. So first we're going to subtract the 2. And this would give us negative x plus 1 cubed is equal to negative 27. Next, I have to divide by negative 1 to cancel out that negative. So now I have x plus 1 cubed is equal to 27. In order to cancel out this exponent, we are going to have to apply the appropriate radical. You know how, let's say, if you had x plus 1 squared is equal to 27, you would square root both sides. But this is not squared. This is cubed. So we have to cube root it. So it looks like a square root, but it's not. It's a cube root. So we write this little number 3 right here in that little space, indicating that it is a cube root. Now the cube root of a number, right? Well, first of all, this cancels out with the exponent, and we have to do the same thing to the other side. Okay, so we have x plus 1 is equal to the cube root of 27. To cancel, or rather to figure out what the cube root of 27 is, the same thing as with the square root. Even though we don't see it, this is a 2. And that's this little number here attached to the radical, that's called the index, which lets you know what kind of root it is. So if the index is 3, that means that we need 3 identical numbers in order to remove it from the radical. Just like here, a square root, even though we don't see the index is 2, meaning we need 2 identical numbers to remove it from the radical. So we break this number down just like we do with square roots. The 2 numbers that multiply to give you 27 are 9 and 3. 9 can be further broken down to 3 and 3. So here are my 3 identical numbers with nothing left over. So the cube root of 27 is 3. So far my equation is x plus 1 is equal to 3. So now, of course, your final step is to subtract the 1. So x would equal to 2. Now it's important to note that when you square root something, your answer is always plus or minus, because 2 identical numbers would multiply to give you whatever is inside. So like, for example, the square root of 4 is equal to plus or minus 2. And that's because 2 times 2 is positive 4, as well as negative 2 times negative 2 is equal to positive 4. We learned that with square roots, you cannot have a negative inside because there are no 2 identical numbers that would multiply to give you a negative, because one would have to be positive and one would have to be negative. However, with cube roots, you are allowed to have a negative because there is such a thing as 3 identical negative numbers that would multiply to give you a negative. So basically, when you have the cube root of a number, the answer to that cube root is whatever sign that number is. And we're going to see that in this particular example. We have here the 2x minus 2 cubed plus 4 is equal to negative 50. So first, I would subtract the 4. And that would give me 2 times x minus 2 cubed is equal to negative 54. Next, I would divide this 2. So x minus 2 cubed is equal to negative 27. Next, I would cube root both sides here. So x minus 2 is equal, now we have a negative inside of this radical. That means that my answer will be negative. We already found the cube root of 27 over here, which is 3. So the cube root of negative 27 is negative 3, and that's because negative 3 times negative 3 is a positive 9, and then times that third negative 3 gives you that negative 27. So now our final step here would be to add the 2. So x would equal to negative 1. We're going to now put all of this together. So here we have this equation, and first we're going to graph it, and then we're going to find the solution to the equation using the graph. Once we found our solution, we are going to confirm that solution by doing the algebra. So first, we're going to write our rule for our transformed function here. The rule for the x's would be x plus 2. And the rule for the y's would be negative y plus 1. Our reference points are negative 1, 0, 0, and 1, 1. When we plug in those points, negative 1 plus 2 is 1, and then negative 1 becomes a positive 1, plus 1, 2. When we plug in 0, 0, 0 plus 2 is 2, and 0 plus 1 is 1. Finally, we plug in 1, 1. 1 plus 2 is 3. Negative 1 plus 1 is 0. Let's go ahead and plot. We have 1, 2, 2, 1, and 3, 0. So my graph is going to look something like this. Now this 2, that's what my equation equals to. So I'm going to draw a horizontal line along y is equal to 2. My solution is where they intersect, specifically the x value. So my solution here is x is equal to 1. Now we're going to confirm this answer by doing the algebra that we just learned. So negative x minus 2 cubed plus 1 equals 2. First, I'll subtract the 1. So negative x minus 2 cubed is equal to 1. Divide the negative 1 to cancel out that negative. So x minus 2 cubed is equal to negative 1. Next, we cube root both sides to cancel out that exponent. So we have x minus 2 is equal to, now the three identical numbers that multiply to give you negative 1 is negative 1. Remember that because the sign is negative, my answer will be negative, and three identical numbers that multiply to give you 1 is 1 times 1 times 1, so 1. So now our final step, add the 2. So my final answer is x is equal to 1, which is what we got here with the graph. So everything is good. Let's try that one more time. We have here parentheses 1/2, parentheses x plus 1 raised to the third power minus 2 is equal to negative 3. First, let's write out these transformations. Because of this 1/2 is inside of the outermost parentheses, that affects the x, so we have a horizontal stretch of 2, since it's always the opposite of what it says. This plus 1 means that it went to the left 1, minus 2, down 2. Now we're going to graph the cubic equation, or rather the cubic function, and then we'll draw that horizontal line. So the rule for my x's here would be 2x minus 1. And the rule for the y's is y minus 2. Using the reference points we've used before, negative 1, 1, negative 1, negative 1, 0, 0, and 1, 1. We plug them in. 2 times negative 1 is negative 2, minus 1, negative 3. Negative 1 minus 2, negative 3 as well. When we plug in 0, 0, 2 times 0 is 0, minus 1, negative 1, and 0 minus 2, negative 2. Lastly, when I plug in 1, 1, 2 times 1 is 2, minus 1, 1, and 1 minus 2 is negative 1. Let's go ahead and plot these points. We have negative 3, negative 3, negative 1, negative 2, and 1, negative 1. So my graph would look something like this. This is supposed to equal to -3. So I'm going to draw that horizontal line here at y is equal to -3. And my solution is x is equal to -3. Now let's confirm that using the algebra. So we have this double parentheses situation. First, we would add the 2. So we have parentheses 1/2 parentheses x plus 1 to the third is equal to -1. Now this exponent here is on the outermost parentheses. So we have to apply the cube root first before I can cancel out that 1/2, since the 1/2 is inside. So we cancel out the exponent, and now we can get rid of this one parentheses, and it's 1/2 parentheses x plus 1 is equal to, and we saw that the cube root of -1 is -1. Next, we would multiply the 2 to cancel out the fraction. So x plus 1 is equal to -2. Our final step here, subtract the 1. So x is equal to -3. And we have now confirmed our answer. And those are cubic functions and how to solve cubic equations.